Hi, my name is Daniel Bittman. Today I'd like to talk to you about our vision for untying ourselves from the limitations of RPC. Building large, complex systems is hard. One way that we can make these huge engineering challenges tractable is through decoupling. So while we might have a huge monolith application, at least we can reason about the individual pieces. But scaling these big monolith applications is also hard. So what we do is we take those pieces and we split them up amongst a bunch of different machines. To do this, we use RPC as the glue that holds the system together, enabling this interaction of components wherein I ask a particular server to perform some computation and return me the result. And this is great. It has some really nice semantics, in particular, moving a computation around the system to where it might be best executed. The problem, though, is that we've moved away from a programming model that focuses on data, which is the thing that's driving the computation, and instead makes machines and hosts the first-class citizens. And this only really works if I've been able to divine ahead of time the correct decoupling for my compute and my data, such that the computation that I want to run and the data that it operates on can be co-located on a single machine. This kind of rigidity causes programmers to root the design of their system around a decoupling that's difficult to evolve as the needs of the system and its uses change. So in a minute, I'll go through a concrete example involving an inference task, but it's not that hard to imagine simple scenarios that make this limitation not just theoretical. For example, an endpoint might have abundant compute but little data, or the opposite, it might have very little compute but all the data necessary. The fundamental problem is that RPC is a location-centric model wherein we use call by value for arguments and return data. We need a more flexible model of decomposition in distributed systems, wherein we can use data and references to data that don't rely on some host-centric format. After all, what if the data were to move? But where we can still get the nice code mobility aspects of RPC. Now, some of the veterans might be rushing to the chat to try to wonder aloud if we're just trying to sell everyone on distributed shared memory. And, well, yes, well, sorta. Look, there has been some renewed interest in DSM due to technology trends like faster networking hardware and smarter switches. In fact, I don't think that reconsidering DSM designs today should even be that controversial. But DSM is only half the picture here. It still ends up with a similar rigidity, and it only provides a model for data movement and not code movement like RPC provides. The key to our vision is to combine the code mobility of RPC with the data mobility of DSM inside of a global address space where any data can be pointed to from anywhere regardless of any local context. This allows applications to invoke functions without the inefficient call by small value semantics of RPC. We plan to realize this through an operating system and network co-design, where all levels of the system understand a common language for data references. So let's ground ourselves in a concrete example. Let's imagine we have a device, like an edge device or a mobile phone, that is in possession of an activation and wishes to perform some inference task. This involves executing an expensive computation on some large amount of data. And this is an important problem, one that is growing in size and scope as model sizes continue to grow. So let's consider a situation where our device, who we'll call Alice, has the activation, but due to memory and storage constraints, doesn't have the full model. Instead, that model is stored on some cloud device, who we'll call Bob. Now, Bob has ample storage for the model, but let's say that Bob is overloaded. Next, we'll also consider another cloud device called Carol, who is not in possession of the model, but is underutilized, and would happily perform the inference task if only she were in the possession of the data that's stored on Bob. So look, the naive solution here is to just say, well, Alice knows the data that's needed for her computation, so we can just have her copy the model over from Bob, and then copy it over to Carol, and then perform the RPC to make Carol do the inferencing task. So instead, we can try to optimize this by implementing a special RPC on Carol so that Alice can tell Carol to go get the data from Bob before starting the inference task. But in both of these cases, we've put the onus on poor Alice to perform this infrastructure level task of moving data around. Instead, we want to do something more like this, where the call to Carol refers to the model data by reference. If the system is made to understand data references, then the system can move the data around instead of having Alice do it. The fact that we submit our request first before moving data in prep, unlike the two previous examples, is really important because it opens the door for the system to perform optimizations because it knows what's being asked of it in full. And more importantly, it simplifies the application logic on Alice because Alice doesn't have to marshal data around the system. But how will we handle those references? And how will the system understand them if not for falling back to some piece of middleware that keeps us tied to a location and host-centric model? Well, let's talk about another related problem, serialization. Serialization is common when moving data around systems, but it's expensive. It's not uncommon for systems to spend 70% of their time serializing and deserializing their data as it's moved around the system or loaded from disk. But if you squint at this, you'll see that this is really just the same problem as references in RPC. In both cases, we've had this problem of creating long-term data references that outlive the context that they were created in. On the RPC side, we pass values because our systems aren't designed to have pointers work when they refer to data across a machine boundary. And similarly for data structures, pointers in a virtual address space are tied to that space. And so persisting a data structure or moving a data structure across machines involves complex, costly serialization. The solution to both that we propose is a global address space of data, such that data structures can be composed of pointers that are invariant of any local context. This naturally leads to a DSM-type model, wherein applications running on machines don't refer explicitly to other machines, but instead talk about data and computation. If we combine this with a model of data references understood not just by the application, but by all levels of the infrastructure, then we can open the door to reducing application complexity by factoring out common infrastructure level tasks, and perform larger scale optimizations as part of the infrastructure. And perhaps most important, the flexibility that this model affords us improves both the code mobility of RPC and the data mobility of DSM, since now we can move both whenever we want to wherever we want. Computation in this world is just a rendezvous between code and data. In the interest of time, I'll just briefly describe our implementation plans. To realize a global address space and a programming model that directly supports such a construct, we plan to leverage Twizzler, an operating system that we've been developing for some time now at UC Santa Cruz. Twizzler provides the notion of a persistent pointer and a large address space of 2 to the 128 objects, each of which can hold a significant number of pieces of data. These pointers, however, do not cost us significantly in terms of performance nor space because Twizzler has an efficient indirection and encoding scheme. We plan to combine this work with protocols designed for memory accesses and smart switches that allow us to switch on object address instead of machine identity. The paper, of course, goes into more details on this. So instead of showing some initial results here, which can be found in the paper and which demonstrate the feasibility of our approach, I'd like to instead talk about some of the challenges that we'll need to face. The first is our network and OS co-design. Clearly, this is an ambitious undertaking, but we have that ambition and motivation. Let me limit the scale here, though. We're not trying to redesign the entire internet. Instead, we're focusing on smaller, more concrete goals. Nevertheless, one of our reviewers reacted to our co-design by saying, "Who would do such a crazy thing?" But they also described it as a feature and they marked accept in their review, so I'm taking that as a positive. The next clear challenge, as is inevitable in any distributed system, is dealing with the tension between fault tolerance, transparency and abstraction, and the specter of partial failure. Overhead and consistency are the two chief concerns to worry about here, and while these will keep us busy for a long time, we plan to attack the problem on two fronts. First, since we're co-designing the network and the operating system, we plan to leverage recent work on using the network to assist in arbitration. Second, we plan to explore how a programming model built from a global address space and invariant references meshes with patterns for weakly consistent replication and/or progressive objects like CRDTs. So how far along are we? Well, we're currently in the process of implementing this vision, but we're excited to see how it goes and to be in a position soon where we can start answering some of the tougher questions and start leveraging some of the exciting new hardware. We're witnessing a convergence of trends. Software demands are growing, networks are getting faster and gaining richer semantics, and operating systems are providing new ways of accessing data without the complexities of POSIX. If we do it right, we can leverage these trends to support newer, simpler applications that leverage the good parts of DSM and content-based networking, ideas that were previously discarded but can be reconsidered under a new light. We'll realize our vision by combining new OS abstractions with networking support for global references, so that we can factor out complexity into the infrastructure, thus freeing programmers from having to manually marshal data around the system. And instead, they can focus their talents on orchestrating a rendezvous between their code and their data. Thanks for watching, and thanks for making it to the end. I'm looking forward to hearing questions, complaints, and comments from everyone.